Okay, let us see circuit analysis. Now we have, okay, let me just close it for the time being. So now this is a circuit given. We have been asked to find out the value of Vg to keep the MOSFET at verge of saturation. Again, when it is verge of saturation, VDS happens to be VGS minus VTO. Now there is one twist we need to be very careful. This VD is not VDS because this VD is actually VDS plus this drop. So that's why when you're writing the equation, so this to this voltage difference is VDS. So that's why this VD is not equal to VDS. So if you write the KVL expression here now, applied voltage VD, D is equal to ID into RD, that is this drop, because this is the current ID flowing here. ID into RD plus VDS, that's what is this, plus VDS, and the same ID current flows here also, because there is no path other than this, so it has to go around here. It has to go through RD as well as RS, so that's what is this. I'm rewriting this expression as VDS plus ID into RD plus RS. So from this we can write VDS, rearrange this entire equation to VD minus ID into RD plus RS. To keep the MOSFET in saturation, then this has to be VGS minus VTO. Then we are substituting what is the value of ID, which is half Kp W by VGS minus VTO whole square, and this value. So upon substituting all these values, let us see how much we'll get it as VGS. So now let me see. Let me open the parenthesis. Let me write it the way how I'm doing it. So open the parenthesis. This is alpha A. Sorry. Open the parenthesis, alpha A minus 0.4. Close the parenthesis. Alpha equals 1.8 minus. Okay. Maybe let me just redo it. It was not okay. Now this is what, okay, we're just doing with open the parenthesis 0, sorry, open the parenthesis alpha A minus 0.4, close the parenthesis, alpha equals 1.8. okay, it's not required. 1.8 minus 0.5 into 200 exponential minus 6. W by L is 25, so you can take W by L is 25 into 25 into again alpha A minus 0.4 whole square into, this is 1.8k plus 100, it is 1.9k, 1.9 exponential 3. Then shift cal. Okay, you got, just a minute, let me just verify. Okay, this is one of the values. Since it is coming as negative, so okay, one of the values minus 0.432 volt. This is one of the value. So this cannot be a value because VGS cannot be negative. So let me find the other value. To find the other value, equate this to, hey, just a minute. Okay, let me do shift cal. I got it as this. Then you make it equals. So I'm pressing equals and type some larger number. 10 n equals shift cal. So I'll get one value. So the other value is 0.969. So this is the voltage of, this is the other voltage. So let me just find out, this is the other value. So this is 0.6, 0.8, oh sorry, here this should be 25. I just kept it as 20. So let me just type this. W bar is actually 25. Let me do shift cal. So there is something wrong in my entry. Actually W bar is 25. So what I'm getting is 0.919 is one of the values. The other possible value is, to get the other value, simply say equals some negative value, some minus 2, alpha equals shift cal. So it is minus, this is not minus 0.329 volt. So there are two voltages, one voltage 0.919, other voltage is minus 0.329. So this cannot be a valid value, so this is a valid one. So this is the value of VGS. So now this VGS will give me some current, because this is the voltage required here should be 0.919, but we are asking what is VG. So VG is nothing but VGS plus ID into RS. This is the actual value of VG, that should be. So this is the value of VG, which is nothing but VGS plus ID into RS. What we actually found was this. So 0.919 is actually this voltage. I should know what is this voltage. So for which I should know what is ID. So what is ID now? ID is equal to half Kp W by L VGS minus VTO whole square. So this is the value of VGS 0.919, and let us find what is ID. So it is now 0.5 into 200 exponential minus 6 into 25 into 0.919 minus 0.4 whole square equals, so it is now 673.4 microampere. So this is the current that multiplied by 100 is ID into RS plus 0.919 is VGS. So then this happens to be 0.986 volt. This is VG. So VG has to be 0.896 to operate the MOSFET at verge of saturation. So let us verify the same thing in this. Let me open that. So this is my circuit. Okay, let me close this. See, I have RD as 1.8k and this has 100 ohm and this is 1.8k. This I'll going to sweep. So this cannot be 1 volt. So I'll going to sweep this using simulation command .dc, which is now VGS now. Okay, VGS, it's not case sensitive. I'm starting from maybe 0.6 volts to maybe up to 1 volt with an increment of 0.01. If I do this and do .op, okay, .dc is there, this is enough. If I run it now, let me see what is the voltage here. Okay, let me see how much is my OW bell. Should be 25. Okay, it should be 25. This is fine. This should be 1.8k. This is 205. Now let me rerun this. Okay, let me just still run it up to maybe up to 2 volts. Maybe up to 1.5 volts. Let me run. Okay, now we will just track this. So at a voltage equal to 0. This is actually VG. So when VG is equal to 0.986, so that is at 0.986 the VDS will be, so what will be VDS I'm looking at? So VDS is equal to what? 0.919 minus 0.4, which is nothing but 0.519 volts. So this is VDS, so I have to measure differential voltage. Be careful here. Whenever you just press this voltage, okay, let me just show you that. Suppose what the voltage that I'm measuring is actually VD here. So this VD is actually VDS plus this one. So what I want to know is only VDS. So let me just take out this. I don't want to have this. So I want to measure VDS. So to measuring VDS, what you have to do is click on this drain and hold this and stop it at, put it at source. Now this is the differential voltage. So now this is actually VDS. So VD minus N002 is actually VDS. N002 is this terminal. If you measure this voltage, when it is, this is actually VG, when it is 0.9986, let me just show you that. So when it is, 1 second, when the value of VG is 0.956, the VDS will be 0.519. I'll show you that. So we are looking at, 1 second. Okay, I'll just keep on moving this. When VG is equal to 0.986, so this is 0.986, 0.986. So you concentrate on this 0.986, this 0.986. Are you there at 0.896? I just go there. Okay, 0.896. I'm almost there. Can you see? Let me just slightly go back. Okay, I'm here now. So this is 0.986. At that point, can you see what the voltage? So we are supposed to have 519 millivolt. I'm having almost 521 millivolt, hardly 2 millivolts difference. Hardly 2 millivolts difference. At this value of VG, that is at this value of 0.896, the VDS is 0.519, which is what I'm having. So what is the corresponding value of VGS at this value of VG? It will be 0.919. So that also we can see. So what I'll do, I will measure VGS, which is from here to here. Now if you carefully observe this, at 0.986, can you see how much is this? So this was supposed to be 0.919. Don't you have this as, this was actually 19 millivolt, you have 918.8 millivolts. So at this VGS, sorry, at this VG, you have this much VGS. So 100 millivolt difference is there, 100 millivolt difference is there. So that's how you can able to verify this theoretical calculation with the simulation results. Thank you.